Section 5.1. First thing we're going to do is define a little phrase here, and then we're going to talk about it a little bit more. This is called a perpendicular bisector. And, oops, I need to change this and change this. Alright, so let's write that down. Perpendicular bisector. Perpendicular. Now, we've talked about both of these words. I just don't know if we've talked about them at the same time. But perpendicular bisector. Alright, so let's see what that would be. We'll just start off pretty easy and just make this horizontal. It doesn't have to be horizontal. This line segment could be, any direction. But we'll just make it horizontal for right now. And let's make this next one red. If I wanted to find the perpendicular bisector of this, well, first of all, perpendicular means you're going to have another line. You're going to have another line segment that's what to this line? Perpendicular. Perpendicular. Perpendicular, right? So it must form what kind of an angle? 90-degree angle, right angle, okay? But it also has to bisect. So this is a line segment right here, okay? Let's go back to white. So this is a line segment. So I'll put dots on the end to represent it's a line segment. Everybody good? And I want to draw a line, or you could draw a line segment. It could be either one. That is perpendicular to this line, but also bisects this line segment, okay? So first of all, let's figure out where it's going to bisect it. All right, so on this little program, if I click it, it gives me this. And these dots right here are in the middle. So that would be my midpoint, right? And so that's where it's going to bisect. So right here. Now, how am I going to draw it? I'm going to draw it like this. I'm going to draw it like this. How am I going to draw it? Okay, let's not say straight, because this was straight, right? That's a straight line. That's a straight line. But let's say perpendicular, right? Let's say perpendicular. Now, you don't have to start it right at the original segment. I mean, it could have gone like this, couldn't it? As long as it does what? As long as it bisects it, right? So that must mean that this segment right here is equal to this segment right here. Would you agree? All right, because we're bisecting a segment. Can you bisect a line?
No.
That's right. Line has no beginning, no end. So technically, if you think about it, like every point kind of would be a bisector, wouldn't it? On a line, because there's just as many points to the right as there was to the left, no matter where you are on the line. Would you agree? Okay, but on the line segment's different. It has one midpoint, and that would be it right here. So right now we've bisected this. Now to make it perpendicular, we put a little right angle symbol, and that means it's perpendicular. Let's change the color of this. So there you go. All the stuff in red right there indicates that this thing is a perpendicular bisector. We good with that? Now again, the original segment doesn't have to be nice and horizontal like that. We just drew it like that to make it look a little easier. It could have been slanted. But no matter if it's slanted or not, this red one has to be perpendicular. It has to form a right angle with the white one. We good? So that's just a little preview. It's just something to get us going to the next little thing that we're going to do. All right? All right, now let's do this. Let's move on. Since we know what a perpendicular bisector is, let's take a okay, let's draw another perpendicular bisector here. And I'll go back to the same color coordination. So we have a theorem. We have two theorems, actually. One is the converse of the other one. So if then, remember, switch it around. If P then Q, then if Q then P. Both of these things are true. So here's another line segment. So I'll just put some points at the end of this thing right here. And we'll label it so we can talk about it. All right, so there's the line segment, and I want to make a perpendicular bisector to this. So let's do the same thing that we just finished doing. So I find out where the midpoint is. It's about right there. And then it's perpendicular, so I'll make it like this. Now you could have it go all the way through, and that would be okay. Yeah, let's just make it go all the way through, like this. Now,
Point, like if you click on the line, why are there 2 points in the middle to make it right?
Let's see. Whoops. I don't know if I've tried that. Nah, I guess it just moves it. I don't know why there's 2. I don't know. But like, I don't know about the lines. I think you just move it left and right, up and down. But like if it was like a rectangle or something like that, right? And you see the 2, and then you take one of them, right? And then it moves it like that, right? Yeah, it doesn't seem to make it thicker, but I could always come up top here and make it thicker. But anyway, so there we go. So we've got a line, and if this is true, now I can say that line. Let's see if they label it. Yeah, let's call this CD. C, and then D, where that hits right there. So what can I say? I can say that line CD is a perpendicular bisector of what? Line, not line AB, line segment AB, all right, because I put dots here and it ends, starts and ends at those dots, okay, those points. So this is a line, this is a perpendicular bisector. Would you agree? Now, it's not just like a line can be a perpendicular bisector. You could have a line segment that's a perpendicular bisector, couldn't you? All right, I could have stopped it, you know, here and here, or here and here, and as long as it hits it at the midpoint, and as long as it's a right angle, you could have a line segment that's a perpendicular bisector. You could also have a ray as a perpendicular bisector if you wanted to. I just chose to have a line. Is that all right? Okay, now here's what this thing tells us. Let's do this part in another color. This thing says, if you have a perpendicular bisector of a segment, watch this. Let's start anywhere on here. I could pick any point wherever I wanted on this line right here. Let's just pick point C, all right? If I did this, watch this. If I draw from here to the end point of my segment, and I draw from that same point C to the other end point of the segment, take a wild guess on what may be true about those two red lines right there. They're equal to each other. So what it says is this. This is on page 322. It says, if a point is on the perpendicular bisector of a segment, point C, is point C on a perpendicular bisector of a segment? Absolutely. Then what's true about it? It says then it's equidistant from the endpoints of the segment. So that means it's equidistant from the endpoint. So from C to one endpoint, and then from that same C to another endpoint, they must be equidistant, which means those two lines have got to be equal to each other. So this and this will be equal. And that's a theorem. It's called the Perpendicular Bisector Theorem. All right? Pretty good. Does that make sense? So that's, you can write it in here, I'm not going to, but it's called the Perpendicular Bisector Theorem. So what does it say? It says if you already have a perpendicular bisector, if we already know that we have a segment, all right, that's split down the middle, if you want to call it, all right, and at a right angle, if it's a perpendicular bisector of this segment, then any point on that perpendicular bisector is equidistant from the endpoints of that segment. All right, it's a lot of words, but if you think about what I'm saying, it makes sense, doesn't it? And it kind of shows in that picture. Look, I could have gone anywhere. Is it just point C? Is that like the magical point? No. I could have picked a point down here, couldn't I? Watch. If I would have picked a point, it's got to lie on the line. Oops. Watch. If I went from here to where? To A, and then I went from the same exact point to what? B, then those two are going to be equal to each other. Now, are these two yellow ones necessarily equal to the two red ones? No, they're not, but they are equal to each other. Does that make sense? So I could do this all day, couldn't I? Picking points. If I wanted to, look, I could have picked a point below here, couldn't I? I could have picked a point like right here. And what's true about this point? Well, it's equidistant from the endpoints of that segment. So those blue ones would be equal to each other as well. Does that make sense? All right, we good with that? What do you think the converse says? Now this says, I'll tell you what, let's do this in red. The statement itself, or the theorem itself, says if you have a perpendicular bisector, I'm really shorthanding this. Okay, if you have a perpendicular bisector, then a point on the perpendicular bisector, or then a point is what? Equidistant from the endpoints of the segment. From the endpoints. Oops, running out of room. From the endpoints. I kind of shortened it quite a bit, but you get the idea. Endpoints. So if you have a perpendicular bisector, then what's true? Then the point, any point on that perpendicular bisector is equidistant from the endpoints of that segment. That's the if and the then. What do you think the converse of this would say? Okay. You got it. Watch this. Well, not just perpendicular. A little bit more than that. It's a perpendicular bisector, exactly right. So let's start with this information right here. If you want to redraw that, you can. I just erased those things. Now look, according to this picture right now, is CD a perpendicular bisector of AB? Not with the information that we know right now, is it? Okay, because I don't know that AD and BD are equal to each other, do I? And I don't know that at angle D right here, I don't know that's a right angle. But what do I know? I know that a point on this line, and I can't call it a perpendicular bisector just yet because I don't know that it is, but I have a point on this line, and what do I know about it? It's equidistant from what? The endpoints of the segment, right? Okay, so this is, remember, this is the converse of it. If Q, then P. So this says if you have a point that's equidistant from the endpoints, okay, of a segment, then it must lie on the what? What do you think? On the perpendicular bisector. If you want to jot that down, you can. I'm just not going to. I'm standing up today. It's hard to write when I stand up. So if you have a point that's equidistant from the endpoints of a segment, so if a point is equidistant from the endpoints of a segment, a line segment, then that point lies on what? The perpendicular bisector of that segment. Okay? So would you agree now? Now with this information and with this theorem, this is the converse of the perpendicular bisector theorem. So if you have this information right now, our theorem says if this is true, if this line segment CA is equal to this line segment CB, then point C must lie on the what? Perpendicular bisector. So if it lies on the perpendicular bisector, what then can we say about this? We can say that we have a right angle, and we can also say that AD equals DB, or BD. Do you see the difference? It's all what they give you at first. At first, they told you the thing was a perpendicular bisector. Then we could have said those two red lines were equal to each other. But the second one said, okay, it didn't say it was a perpendicular bisector, like the converse of it, but it did say the two red ones were equal to each other. Well, what does that mean? That means that that line right there, CD, is a perpendicular bisector. See the difference? This is not the first time we've done the statement then the converse, is it? If P then Q, or if Q then P, right? We've done that before, and you'll see a lot of that in the future. All right, enough of that. They give an example for that. If you want to look on page 323 and actually look at the example and go through it, just for time's sake, we're not going to go through that example, but it's pretty straightforward. Now, we've actually done two things leading up to what we're going to do right now. All right, so the two things that we've talked about before, we basically just did it so we can do this next thing. All right, so this next thing's pretty important. Tell you what, for this next thing, I'm going to want a triangle. So let's come up here and grab a triangle, copy it, and paste it. You can use any triangle. I just picked this one. What we're going to do right here, let's make this a little bit bigger, just so I can really work with it here. And let's make it a little thicker. Okay. Make it as big as you want. Okay, but we're going to draw a bunch of stuff inside of there. So I just wanted to give me some room. I just didn't want it real tiny. Okay. So what I'm going to do is this. I'm going to take this triangle, and I am going to draw a perpendicular bisector of all three sides of this triangle. And something kind of magical happens. I don't know if I'd say it's magical, even though I did say it's magical, but it's it kind of is. All right, it's kind of cool. Watch this. Let me ungroup it because I want to just pick this. Yep. So what I'm going to do is I'm going to draw the perpendicular bisector of all three sides. So let's take this bottom one. That's the easiest one. So if I do the perpendicular bisector, I think the most important thing is to find the midpoint first, right? So I find the midpoint. It's right there. All right. So I keep my little dot right there. And then I'm going to draw it so it's perpendicular to this, right? And I can go up as high as I want. I don't care. I'm going to move them a little bit later, but I'll just make it go up like that. If you wanted to stop at the side, you could. But I'm just going to make it go up pretty high. So now, it's not a perpendicular bisector yet, is it? Well, that's half of it. Now it's perpendicular. How do I know if it's a bisector or not? Actually, I'm going to do this in a different color. Is that all right? So these stand out a little bit. Let's do this in yellow. All right, so now, do I know it's a perpendicular bisector yet? Not yet. Now, is it a perpendicular bisector? Absolutely. Okay, it's a perpendicular bisector. So let's do that with the other two sides as well. All right. So if you come over here, that looks about the midpoint right there, doesn't it? Now I'm going to have to eyeball this a little bit to see if it's if it's perpendicular. Does that look kind of perpendicular? Like maybe like that? About right there? Perpendicular to this side right here. And let's just change it back to yellow again. All right. So that kind of looks perpendicular. Had to eyeball it a little bit, but that's okay. And then that must mean that these two sides are equal, or these two segments are equal. That doesn't look like much of a perpendicular thing, does it? Let's kind of make it look a little bit straighter. There we go. All right, now what do we have to do? We have to do that to the other side, don't we? So let's go to the other side. Let's find where the midpoint is there. It looks about right there. Now, this is what I was talking about. This is kind of cool. Watch this. If I draw a line that's perpendicular to it, guess where it's going to go through? Yeah, sure it is. That's perpendicular. Perpendicular to this side right here. It's perpendicular to this side right here. Absolutely. Yeah, I would say it's perpendicular. Okay. All right, so this right here would be a right angle. And this side would equal this, or I should say segment. This segment should equal this segment right here. I'm not going to put letters in here. I'm just going to show it. If you want to put letters in there, you can. Sometimes too much stuff in there gets in the way. All right. Now let's do this. Our perpendicular bisectors, you know how I extended it way out like this? Let's make this a little bit cleaner, and let's just take it. Where do you think I want to take it to? You think? Yeah, how about that point right there? Exactly right. Okay, that's a good place to take it. And let's take this one right here, and let's just take it to that point where they all intersect. And let's take this, yeah. You can just erase it, right? If you wanted to, use your eraser. Okay, that's pretty close. And look what they do. They all meet at one point, don't they? We have a couple words here. Anytime you have three or more, I think they say three or more. I'm not sure. Let me see the word. Yep, it says anytime you have three or more lines that meet, that intersect at the same point, we have a special word for that. You want to probably jot that down. Anytime you have three lines that intersect, three or more lines that intersect at the same point, we call those lines concurrent lines. All right, they're concurrent lines. Again, you might want to write down a little bit more. They're anytime that three or more lines intersect at a common point. Okay, if they have a common point of intersection, three or more lines, we call those lines concurrent lines. Okay? I mean, two lines, if they intersect, we just call them intersecting lines, right? But if you have more than that, if you throw a third one in there that intersects in the same spot, then we'll call them concurrent lines. Got it? Now, on this particular thing, if I have a triangle and I did the perpendicular bisector thing, they all intersect at that one common point right here. All right? We call that thing a circumcenter. Circumcenter. Now we're going to learn probably about three. Did I spell it right? Circumcenter, yes. We're going to learn about three, maybe I think three or four. I forget exactly. Maybe three, maybe four. I think four. Four different words that do this. We have several different ways that lines are concurrent inside of a triangle like this. This is one of them, circumcenter. I tell you the truth, be honest with you, sometimes I get confused between which one is which. All right. But there is something a little bit more special about this. So this is called a circumcenter. How do we find the circumcenter? You do what? You probably want to jot this down in your notes. How do you find the circumcenter of a triangle? You draw the what? The perpendicular bisectors of all three sides. Okay. So write that down. If you draw the perpendicular bisectors of all three sides of that triangle, you'll get the circumcenter. Now you got to be sometimes pretty careful, right, to make sure that they are right angles. And if they are right angles, and if you do hit right at the midpoint of each of those sides, then they will always meet at a common point. Everybody see that? If you're just real sloppy, they may not meet, but you got to be pretty careful, and then they're going to meet right there at a common point. Now, there's something. If you draw the perpendicular bisector of each side of this triangle, it's going to meet at a common point, which is called the what? Circumcenter. So the circumcenter is that point right there. Everybody got it? Now we're going to learn about four different words, okay? And that's the first one that we're going to learn. But we're not just going to stop right there. Okay, so they meet at a common point. That's kind of cool already, but this is even cooler. Watch this. If I did this, if I took this circumcenter, this point where they all intersect, and I drew a line up to this vertex, and then I drew a line to this vertex, and then I drew a line to this vertex. What do you think might be true about those three red lines right there? They're going to be equal to each other, absolutely. Okay. Now let's think a little bit about why they're equal. We're going to do a proof, but we're going to do it in our head. Okay, we're just going to talk about it. I'm not going to write down all the steps or anything like that. Okay.
So all of this pieces are equal?
So all the red ones are equal. Now the yellow ones aren't. Okay. Do you see that? This yellow one's way longer than this little yellow one down here. Okay, so the perpendicular bisectors are not necessarily equal to each other, but we say that the circumcenter is equidistant. Jot that down. The circumcenter is equidistant from the three vertices of that triangle. The circumcenter is equidistant from the three vertices. Let's try to figure out why that's true. Well, let's think about this. Let's try to forget everything else except this bottom side right here. What do we have? We got a segment, right? And what is this yellow one? What's this tiny little yellow one right here? That's a perpendicular what? Bisector. What did we say earlier about a perpendicular bisector? Any point on the perpendicular bisector does what? It's equidistant from the endpoints of that segment. Do you see that? Do you see it? So the thing that we did, the perpendicular bisector theorem, works for this, and it's kind of a proof. So would you agree that this red one right here and this red one have to be equal to each other? Yeah, they do, because of that. I'll tell you what I'll do. Well, everybody's got a mark. I'll just put a red mark here, okay? I don't want to start putting 4 and 5 marks here. All right, so according to that perpendicular bisector theorem, this segment and this segment must equal each other. Let's come up here and look at this one right here. Look at this. Okay, what is this thing? This is a perpendicular bisector of this segment, isn't it? And what's true? Any point on this perpendicular bisector, is this a point on that perpendicular bisector? Absolutely. Must be what? It must be equidistant from the endpoints of that segment. You see now it's come together now? All right? Like a glove, right? So that means that this distance and this distance must equal each other. And look at that. All three distances are now equal. You could do the third side as well, couldn't you? This is a perpendicular bisector, so any point on the perpendicular bisector is equidistant from the endpoints of that segment. I know I'm saying a lot of words, a lot of big geometry words, okay? But if you watch the tape, right, the YouTube, you rewind it and think about what I'm saying, you know, it'll start making sense to you, all right? And there you go. That's kind of a proof of why the circumcenter is equidistant from the three vertices of the triangle. That's kind of like a little mini proof. It's in the book, actually, if you look in there. They write it as a paragraph proof. They don't do a 2-column thing, but there you go. All right.
Okay.
Does that make sense?
So what is our homework?
Oh, we're not done. We're not done. We're not done. Let's do another one. We're gonna learn 2 of them today. That was a circumcenter. We're gonna learn another one, and let's use the same triangle. To tell you the truth, on your own, I don't have time in here in class, but on your own, do that circumcenter with a right triangle and do it with a obtuse triangle, and find out where your circumcenter is going to be. All right? You can do that on your own. Jot a little note to yourself on there. Say, tell yourself, just take a few minutes, just find the circumcenter of a right triangle and find the circumcenter of an obtuse triangle. It'll be a little bit different than what we just did. Okay, a little bit. All right? Oopsie daisy. All right, let's do another one. This time, we're not going to do the perpendicular bisector of all 3 sides. We're going to do something else. If I could grab it, there we go. Let's make this a little thicker. Okay, so here's another triangle. Kind of looks the same, doesn't it? But what we're going to do now is we're going to take these angles. Now, this takes a little bit of... I don't have a way to figure out what these angles are. If we had a protractor... If I had an online protractor, I could stick it there and find out exactly what the bisectors are. But that's what we're going to do. We're going to find the bisector. Let's do this in yellow. We're going to find the bisector of each of these angles. So help me a little bit, all right? We're just going to have to eyeball it. We want to bisect this angle. Does that necessarily mean it hits the midpoint of the opposite side? No, not necessarily. But look at this. See this right here? Stop me when you think this angle is equal to this angle. About right there?
No, stop.
Like down?
Yeah, like that.
About right in there? Okay. Now we're just eyeballing, okay? We might have to fudge a little bit on the last one, all right? But if you had a protractor, you could do this, all right? You could, Bisect the angle. So what are we doing? We're bisecting each angle. What do we do on the circumcenter? Wait a minute. What did we do on the circumcenter? What did we do? We didn't bisect the angles. We did what? Found the perpendicular bisectors of the sides. This one's different. Okay, this one, we're going to bisect the angles of this triangle. So let's take this angle right here, and let's bisect that. So tell me when you think it's bisected. Probably around in there somewhere, right? It's pretty close, isn't it? This angle is equal to this angle? A little bit to the right, maybe? Yeah, I think you're right. Maybe about like that. Does that look a little bit better? So does this, I'm bisecting the angle. Listen, taking this angle and I'm splitting the angle into two equal angles. Is this angle and this angle the same? Pretty close. Is this angle right here and this angle right here the same? Yeah, pretty close. Let's do it one more time. Let's bisect this angle. What do you think might be true? Since we talked about that word concurrent, what do you think might be true if I bisect this angle? It's going to hit right there, exactly. Okay? And look, it sure looks like it's bisected, doesn't it? Maybe it's off just a tad, but again, we're eyeballing a little bit, okay? And look what's true. If I bisect all those angles, okay, what's true about those three lines then? All three of those bisectors are what? They're not necessarily equal to each other. Because look, this one right here looks a lot longer than this one right here, doesn't it? So they're not going to be equal to each other. What are they? What's the word? It's a definite, or it's a word that we learned, a vocab word we learned. Concurrent. They're concurrent because they all intersect at the same point. Okay? Does that make sense? All right, let's do this. Let's, you know how I moved them so they just hit where they, at that concurrent point? So let's just move this right there. And let's move this right there. And move this one right there. Okay? That looks kind of cool, doesn't it? So this point right here has a name. It's not called the circumcenter. How do we get the circumcenter? By doing what? By doing the perpendicular bisectors. This is not called the circumcenter. This is called the incenter. Now, I don't have any like fancy way to remember which word goes with what. And sometimes I get a little confused myself. So, but just write it down. So how do you find the incenter? You bisect each of the angles. That's how you find the incenter.
So the circumcenter has the...
Circumcenter is a you find the circumcenter by doing the perpendicular bisector of all three sides of the triangle. You find the incenter by doing what? Finding the bisector of all three angles. You get it? So we're bisecting angles to get the incenter. We bisected sides and found perpendicular sides to do the circumcenter. Okay? So to find the incenter, we bisect the angles. If you want to, you could mark them so those two angles are equal, these two angles are equal, and these two down here are equal. Okay? Alright, that's how we found the incenter. Now look, there's something cool about this. It's already kind of cool that they are concurrent. That's kind of neat that they actually hit each other at the same point. But what's cool about this is this. Watch. Let's do this in red. If I took this incenter right here, and if I found the distance from this point to all three sides, now what is the distance? We talked about that in another chapter. What is the distance from this point to this side? Is it from there to there? Is that the distance? Is it the middle? Is it to the middle? It's what? You said it. It's perpendicular. It's 90 degrees. That's right. Okay, it's perpendicular, okay, to that side right there. So that little thing I just drew is what? That's the distance from the incenter to that side of the triangle. Watch this. What if I did the same thing over here? What am I going to do? I'm going to find where it's perpendicular, correct? That looks about right. Pretty close. Again, I'm eyeballing on this one. So that looks perpendicular. And what about the distance from this point to the other side? Right there. Now, it may not be perfect, okay, because we're kind of, you know, we're trying to eyeball where it's perpendicular. We eyeballed the, you know, bisecting of the angles. If you wanted to be really, really precise, you could use a protractor, and you can use, you know, a protractor is really all you need, right? Bisect the angle, and then go from here perpendicular, right, to make sure it's perpendicular. And look, what do you think might be true about all three of these red lines right here? They're going to be equal to each other, the same distance, right? That's a good way to put it. All right, so they have the same distance or they're equal to each other. So an incenter, how do we first of all find the incenter? We bisect what? Each angle. Okay, they're concurrent, right? At that point right there. And what's true about that point of concurrency? Do you hear that word? How's that for a fancy math word? That point of concurrency. That's where they all intersect. That point where they all intersect. What's true about that point of concurrency? It's what? It's equidistant from the sides of the angle. Exactly right. Do you remember what the other one was? The circumcenter? It was what? It was equidistant from the vertices. Do you see it? So the circumcenter was equidistant from all three vertices. The incenter is equidistant from all three sides. You get it? Now, you know what they're going to do with this stuff, don't you? They're going to stick numbers in there, and they're going to say, okay, if this is 5, what is this? Well, that will be 5, and that will be 5. You know, they're going to do, yeah, they're going to do all kinds of stuff like that. I said this at the beginning of the year. Listen real quick. I said this at the beginning of the year, that each chapter that we go to, really, I don't think each chapter progresses like more difficult. Like algebra, I think it does, okay? But in geometry, I don't think it does. I think we kind of have already learned what we're going to learn in geometry, except we just apply that stuff to different figures and different pictures, okay? It's the same kind of stuff. The math is going to look very, very similar to what we've done in the past, all right? So if you kind of got a grasp of it before, each chapter I don't think gets progressively harder and harder. I really don't. I think it's just different stuff. You're doing the same thing, basically, just with different stuff, all right? That's what I think, anyway. All right, so that's the incenter. Yep, let me give you some homework. And we got everything covered. I can't believe it.
How do you do the ones with like the numbers and stuff?
Well, you'll have to figure those out.
It's really easy.
Actually, why did I split this up into 2 days? I shouldn't have, but anyway, I did. So we'll call it A and B, all right? So it's the first one is page 327. I should add some more problems to this, shouldn't I?
No.
Remember
So
how much
9.
were your favorite class?
Oh, is that what it is?
My main source to come to this thing.
Okay. I'm coming to this thing tonight, too. I'm videotaping it, so I'm here, too. All right, so here we go. There it is. We'll call it Part A because tomorrow we'll do Part B, all right? So 327, 9 to 20. Maybe because I don't know why. Anyway. All right, that's it. Have fun.